Good morning. Hope you guys had a great weekend. We're going to talk about NMR spectroscopy today. I hope to get pretty far. I'm going to be going we're running out of time here, so I'm a little worried. But we'll get it all done. Are there any questions before we get started? Anyone? All right. All right, so let's continue what we were doing last time. I showed you an example of an NMR spectrum, and we're going to hit points, important points, and then we're going to keep going back and adding things to the spectra to show things that we're going to be looking for. All right, so we talked about chemical shift. So the chemical shift for this signal here, 3.4, and this one is 1.8. Chemical shift in parts per million does not change with the instrument. Chemical shift in Hertz does. So we normally are going to indicate the chemical shift with parts per million, or the little delta sign. You can also use Hertz, but generally speaking, we don't use Hertz. So here, to calculate chemical shift, you use this formula: chemical shift equals distance downfield from TMS in Hertz and the operating frequency of the spectrometer. And chemical shifts in parts per million, it does not change with the instrument. Chemical shift in Hertz does change. So when I say with the instrument, there's different levels of there's different magnets. There's the common ones, 60 megahertz. For the very low level instruments, there's 300 megahertz. You'll even see 200 megahertz, 400 megahertz, 500, 700, 800. And this particular NMR was taken on a 500 megahertz instrument. So if we wanted to calculate the chemical shift in Hertz, so let's do that right here for the above NMR. Using this formula, 3.4 equals the distance downfield from TMS in Hertz, which we don't know. It's a 500 megahertz instrument. And so X equals 1700 Hertz. So that would be the chemical shift in Hertz, but we don't normally report it in Hertz because, again, that number is going to change based on what kind of instrument we're using. So if you want to go back and say right here, we'll just do it for the 3.4 peak. This would be 1700 Hertz. But again, we don't normally report it in Hertz because that number is going to change. All right, so we talked about the fact that we have this reference peak in every spectrum, TMS, tetramethylsilane. The protons of tetramethylsilane are more shielded than most organic compounds because they have a higher electron density around them. And this all has to do with electronegativity. So if you look at silicon, it's a 1.8. Carbon is 2.5 for electronegativity. So as you can see, electron density is flowing towards the carbon that's bearing the hydrogens. And remember, we're looking at protons in a proton NMR. So we have electron density flowing towards those protons. So electron density flows towards the carbon bearing the protons. And when protons have a lot of electron density around them, they're shielded. So that means that they're shielded from the magnetic field. So remember our analogy, the big magnets is 500 megahertz magnet is the cold, we're in the Arctic, we're out there, and the electron density around the proton protecting it from that full magnetic field is like wearing a fur coat. Okay, so these are going to be the most shielded from the magnetic field. If you compare that to just a regular carbon-carbon bond, we have 2.5 and 2.5. So electron density is not flowing towards the carbon bearing the protons. So I'm using the word bearing. You could also say the carbon bonded to the protons that we're looking at. So bearing or bonded. All right, so that's TMS. The terms upfield and downfield describe relative locations of signals. Upfield means to the right towards TMS. So pretty much everything is in terms of TMS. And downfield means to the left, away from TMS. Protons that are shielded are moved towards TMS, upfield, and protons that are deshielded are moved away from TMS. So let's label that in this. So I'm going to take this up and I will put it back again. So towards TMS, shielded is this direction going to the right. It's also upfield. Or towards TMS. If we go in the opposite direction, that would be this direction. It's now called deshielded. Or downfield. Downfield, which means away from TMS. All right, so let's go back and talk about the terms upfield and downfield describe the relative locations of signals like we just indicated. What does that actually mean? So here's a way to think about it. And we'll be putting this back up if you missed anything. Electron density near a proton, we'll just write hydrogen, generates a small magnetic field. So electron density near the hydrogen generates a small magnetic field. So here's our giant in that first spectra of 500 megahertz, very powerful. This is a HO, which is the applied magnetic field. And if we have electron density nearby, we can generate a small induced magnetic field, and that's going to happen anytime we have circulating electrons. So this is H induced. And these are vector quantities. So if we have this very large vector here and we have this going in the opposite direction, it's going to take a little bit of that away. Some of that's going to cancel out some of that larger magnetic field. So, and when that happens, the proton feels, they don't feel, but I'm trying to make this accessible here. Proton feels or experiences a smaller field, a smaller effective field. And we call this H effective. And H effective is just the HO applied minus and adding the H induced. So proton feels a smaller effective field. That means it's partially shielded from the magnetic field, the full strength of the magnetic field, right? So that's our fur coat. Shielded. And if it's shielded, chemical shift moves upfield. Which is towards TMS. The more shielded, the more towards TMS. The closer it gets to TMS, it will have a smaller chemical shift. Okay, so if we're at TMS is at 0, the closer we get to TMS, this number is getting smaller. I realize that scale is not very, you can't see that very well, but it's there. So shielded, we're going to get lower chemical shift as these things become shielded. All right, couple more things. The area underneath each signal is displayed in the form of a line of integration superimposed on the original spectrum. So let's put this back up again. You can kind of see it right here. Let me trace over it. That's the integration for that peak. That's the integration for that peak. Okay? So those are the integration lines. All right, so the area under each signal is displayed in the form of a line of integration superimposed on the original spectrum. The vertical rise of the integration line over each signal is proportional to the area under that signal, which in turn is proportional to the number of hydrogens giving rise to that signal. Newer NMR spectrometers automatically calculate and plot the value of each integral in arbitrary units. Okay, so we didn't do that here. Let me see if I brought my little ruler. So one of the things you're going to be allowed to bring with you to the final is a small, clear ruler. So something like this, okay? And you might need that. Sometimes you don't need it. Sometimes you can kind of eyeball it, but sometimes you don't need it. So that's what I'm going to be using to measure this vertical rise here. But we're going to come back and do it. I'm going to leave this one to you. We're going to come back and do that on the spectrum that's on the next page. So here's an example. All right, so MBT is a gasoline additive. If you're looking around at stuff while you're getting gas in your car, you'll notice that that's one of the additives that they add. And so here's an NMR spectrum of MBTE, and we want to figure out what the integrals are. All right, so we know altogether how many protons do we have here? Twelve protons. So some of those protons are represented by this peak, and some of them are represented by this peak. So we're going to figure out how much here, here, and here. And you can sometimes eyeball this. So like what this is looking like to me, if this was 1, remember it's the relative ratios, this is 1, this would be what? 3. So that's one way you can do this. You can actually take a side of a piece of paper, and you can just mark this vertical rise here. I'm just going to go here like that. I'm going to call that 1 unit. And then if I come over here, that's 1, that's 2, and that's 3. So you might not need to use a ruler. So that this is 1 unit, and that's 3 units. Okay, so that does not mean that we have 1 proton here and 3 here. This is relative to the total amount we have. We have 12 protons altogether. So what would this be? 1 to 3, but we have 12. This has to be 12 protons. So this one would be actually 3. And this one would be 9. So we multiply each by 9. So this peak represents 3 protons, and this peak represents 9 protons. That's one way to do it. I want to give you another way to do it, and that is we actually measure this. So I take my ruler out, And I'm just going to say that's 3.3 centimeters. Take this piece of paper away. 3.3. The units do not matter. Just be consistent. That's 3.3. And then I measure this distance here. And what do I have? I have 10.3 here. So that's 3.3. This is 10.3. And to get the number of protons for this peak, I would take 3.3 divided by the total. 3.3 plus 10.3, that's the fraction that involved this peak. And then I would multiply that by 12, the total number of protons for this compound. Total number of protons. And if I do that, I get 2.91, which is approximately equal to 3. You would round this to the nearest whole number, because we can't have fractional protons. Over here, I would say 10.3 divided by 3.3 plus 10.3 times 12, and I get 9.088, which is approximately equal to 9. So 2 ways to get the same answer here. And sometimes you can just glance at it and see, like I could glance at this and see that that was a 1-to-3 ratio. All right, so on your own, I want you to try to do the NMR that that's already on page 175. So we have so much written on that page. Yes?
By number of protons, are you counting the protons in the form of hydrogen, or are you counting the protons that central carbon?
When we say protons, we mean hydrogens. We call it proton NMR when we're talking about hydrogens. Okay? All right, more questions on that one. So this means that we have 3 hydrogens. This is the number of hydrogens giving rise to this signal. And this right here, this is, so this is 3, this is 9, this is the number of hydrogens giving rise to this signal. All right, point number 5, hydrogens in identical environments, also known as equivalent hydrogens, give the same proton NMR signal. So we actually have 4 different types of hydrogens in this molecule here. So the one on the right, 4 different types of hydrogens. So therefore, we will have 4 signals. Let's look at them. And very often, we label them as A, B, C, and D. So this methyl and this methyl here are identical. Okay, remember, we don't have 90-degree angles. This guy's rotating. These 2 methyls are identical. We'll call those HA, and this one HA. And so all 6 of these hydrogens are identical. Next one would be HB. These 2 hydrogens are identical. And then we have these, we'll call these HC. These 3 hydrogens are equivalent. And then we have this hydrogen here is definitely unique. We'll call that HD. So we have 4 different types of hydrogen, so we will have 4 different signals in the NMR spectrum. If you were thinking that this methyl should be the same as this because they're all primary, that would be wrong because we're all talking about environment here. These 2 methyls are in a different environment. This methyl is bonded to a CH2. These 2 methyls are bonded to a carbon that's bonded to a hydrogen and an ethyl. So it's a completely different environment. They are different. They will have different signals. All right, how about this one here? How many different hydrogens do we have?
2.
Most people would say 2. It's actually 3. Okay, so this bond right here cannot rotate. Pi bonds don't rotate. So that means that this hydrogen here is permanently alongside this chlorine. This hydrogen right here on the same carbon is permanently next to this hydrogen. They are not identical. They are in different environments. They're in different environments that can't change by rotation. So we have 3. So no free rotation. Therefore, all hydrogens are unique. So we will have 3 signals. In a proton NMR, we will have 3 signals. All right, so what about this next one here? Careful here, we have restricted, we can't rotate. When we have a ring, those atoms are constrained to be in the position that they're in. They can't rotate away. So how many hydrogens for this? You also want to look for planes of symmetry here. So it turns out this hydrogen on the top is not the same as this hydrogen on the bottom. Because this hydrogen's right next to the chlorine, so is this hydrogen. These 2 hydrogens on top are actually identical. These 2 hydrogens are identical. That hydrogen is unique. So we have, we'll call this one A, HA, those are identical. And then we have HB. And this is all about the plane of symmetry that goes right here and cuts that molecule in half. And then our last type is C right here. That's unique. So again, no free rotation. Therefore, we have 3 different hydrogens. And therefore, we'll have 3 signals. All right. Questions? Yes?
For that ring, what if it doesn't flip?
Those hydrogens are still stuck right next to that chlorine. There's nothing you could do.
Do like a twist boat and...
There is no twist boat, only a 6-membered ring. So 6-membered rings are a little more complicated. We're not going to be talking too much about those where you have different chemical shifts when it's axial versus equatorial. That's for a definitely more advanced class that we're doing. All right, how does the structure of a compound affect peak position chemical shift? This is a chart that kind of gives you an idea. This tells you the environment of the proton. Do I want you to memorize this chart? No, this is actually going with your final. You will have this as part of your final. Okay, so we have the top and the bottom here. So it looks like here we have protons on carbon attached to halogens in this region right here. Proton on a carbon attached to a nitrogen kind of right in this region here. So we'll have this. Protons bonded to oxygen are in this region right here. Big range for these guys, by the way. Big range. Regular alkanes, 0.7 to 1.7. So when we're attached to, when the carbon's attached to electron withdrawing groups, the number goes up, the chemical shift goes up, and it's moved downfield. Hydrogens bonded to oxygen. Okay, so then we have hydrogens, the vinylic hydrogens, 1.6 to 2.8. Hydrogens that are actually bonded directly to an sp2 carbon, 4.5 to 6.0. Okay, and then hydrogens adjacent to a ketone, 2.1 to 2.6. hydrogens that are bonded to, that are part of an aldehyde are all the way down at 9 to 10. So when we have protons that are this far down, it means we either have an aldehyde or we have a carboxylic acid proton. These guys are removed really far down. Most of the time, you'll just see 0 to 10 printed, but if you have this and this, you'll see a larger sweep width there. Okay. Let's talk about where these numbers come from. So the electron density of substituents into compounds affects peak position. Electronegative substituents shift things downfield. They are de-shielding. Okay, so here's our analogy. We're in the Arctic. We have our fur coat on. We have electron density around us. That's the fur coat protecting us from the full cold or the full magnet. That's what we're using for analogy. If you have an electron withdrawing group, what does it do? It pulls electron density away, right? So that's like somebody pulling off your fur coat, and now you're standing in the cold with a t-shirt on, right? You don't have your fur coat anymore. You're going to feel a stronger cold. You're going to feel more cold. If a proton's in an environment where electrons are being pulled away, it's going to feel a stronger magnetic field. That's de-shielding. It moves it away from TMS. So here we have a very clear trend. The more electronegative, we have increasing electronegativity this way. Increasing de-shielding. Chemical shift is getting larger. That means it's de-shielding. Chemical shift moves downfield. Which means to the left, away from TMS. All right, there's a rapid fall off with distance. As the electronegative group gets farther away, the de-shielding effect rapidly decreases. So if we're looking at, always we're looking at the bolded hydrogens, these protons right here, 3.3. When we move this electron withdrawing group further away, it goes down to 1.58. So it falls pretty rapidly. So this is just has to do with the fact that this electron withdrawing group, which I'll call EWG, electron withdrawing group here, electron withdrawing group, further away, therefore we have a much smaller effect. Each additional electronegative group increases the chemical shift by a predictable increment. So if we have one chlorine, we have a chemical shift at 3.1. If we have a second chlorine, it goes up to 5.3. So we're adding about 2. If we add a third chlorine, we're adding 2 again. So we're getting definitely higher. So, and that's, and you compare that to just methane, which doesn't have any, and that has a chemical shift of 0.2. So it's not an even amount here, but you can see we're going up predictably. So each additional, so the first chlorine added the biggest effect, but each one after that was about 2. Each additional Cl adds about 2 ppms, parts per million. In a similar environment, the signal for methyl protons occurs at a lower frequency than the signal for methylene, which in turn occurs at a lower frequency than the signal for a methine. So a methine is a CH, a methylene is a CH2, and a methyl is a CH3. And if we look at this compound right here, we're going to get differences here. So the methyls will be at the lowest ppms here. For these three hydrogens would be chemical shift 0.96, and these guys right here Very close, but different. Chemical shift 1.01. When we go up to a CH2, we jump a little bit. Chemical shift is 1.29. We go up to a methine. That's going to go up even further. Chemical shift 1.883. So not need to memorize these numbers, but know that trend as we go, as we're replacing hydrogens with carbons. That's going to make the chemical shift go up a little bit. All right, so let's go back. I'm going to put this chart up one more time here, and I want to point out a couple of things. So now that we know a little bit more about where these numbers are coming from, you're thinking to yourself, well, okay, I know hybridization effects. So here we have just a regular sp3 carbon hydrogen. Here's this carbon is right here is bonded to an sp2 carbon. That's going to make that a stronger, shorter bond. So this hydrogen here, not surprising that that would be up a little more from an sp3. But what about when we go to an sp2 hydrogen? Hydrogen bonded to an sp2 carbon, higher chemical shift, because we've got, remember when carbon is, has more S character, it's like it's as if it's more electronegative, so it's pulling electron density away. So we would expect that number to go up. And then it goes up even further when we have a benzene ring. That's pretty high. That's a pretty high jump from here to here. And then we think we've got it all figured out, and then we go and look right here. Well, that's an sp carbon, right? This should be, that's too low, isn't it? According to our theory about hybridization, we should go here, and then we should go here, and then this should be up higher, but it's actually lower than the sp2 carbon hydrogen. So that's something we need to explain. There's a very good reason for that, which I'm going to go into the explanation for right now, and that's on the next page. Now, I'm going to describe this feature to you. I will not ask you to describe it, to draw it, or anything. If you shut off your brain right now and you don't want to think about this and you just want to look at your chart, you're going to have your chart, and that's perfectly fine. But many of you like to understand what's going on, so that's why I'm going to talk to you about this. Special effects are seen with protons on pi bonds due to magnetic anisotropy. So that's what I'm going to describe right now. So let's look at benzene. We're going to start with benzene. I talked about the donut of charge already, and I didn't realize I hadn't covered that yet, because you guys kind of snickered at that. That's what I'm talking about right there, the donut of charge. So we know that benzene is resonance stabilized. This much we do know. And we know what the hybrid looks like. So it looks like that. In fact, you'll see benzene, especially in a lot of older textbooks, drawn with just a circle in the middle. That's to show that those electrons are shared equally by all of the carbons. We have delocalization. So if we drew benzene on its side, which is what we have here, if we bold this in, it's bolded, but I'm just going to bold it in a little bit more. Is that showing up? Yes. So we have sp2 carbons all the way around. So here's our sp2 carbons here. So sp2 carbons have unhybridized p orbital. And because we have continuous overlap all the way around. So these electrons overlap sideways. And so this is the overlap right here. We have it on the top, and we have it on the bottom. So it looks like a donut. So that's what we were talking about last time. That's the donut here. And remember, we were talking about this in the context of a nucleophile cannot get in and reach in here and do backside attack, because there's all this electron density in the way. But we do have circulating charge. We call it a ring current. And anytime we have circulating charge, it makes an induced magnetic field. And so this is our circulating charge. And we end up getting an induced magnetic field that kind of wraps around that charge. So we have this donut here, and then we have this induced magnetic field that's wrapping around the donut, making it a bigger donut. And if we look at the direction of that induced magnetic field, in the center here, these are the arrows that's showing the direction. In the center, the arrow's going down, right? That's the direction of those arrows. I think you probably can see them a little more on your sheet. Yeah, those are the arrows. Those are going down. On the outside, these are going in this direction. This is the direction of the induced magnetic field. Here is our applied magnetic field. Here's our induced magnetic field. So what's going to happen on the outside here is this induced magnetic field is going in the same direction here, right? So anything that's appearing outside here is actually going to feel a much larger, it's going to feel a larger magnetic field even than the induced, because this is going to add on. These are vector quantities. That's going to add together. If something is appearing right here in this region of benzene, it's actually going to experience a smaller magnetic field because this is in the opposite direction and subtracting. Okay, so that's what we're talking about here. So in the center, the induced magnetic field is opposite HO, which of course is the applied magnetic field. So what that means is that H effective, which is basically our induced plus that, so the applied, HO plus H effective is smaller. So protons that are in this center area are shielded. The opposite thing happens on the outside here. And this should be smaller. There, forgot that R. Okay? Outside, what happens? Opposite thing. Excuse me? Each H effective.
But they're both H effective, like it's defined by itself.
Oh, no, no, no. I'm sorry. You're right. That's a mistake. This should be induced. Thank you. H induced. Okay, outside, induced magnetic field. Is in the same direction. As HO. So this adds to HO. And H effective is larger. So that what's going to happen is on the outside, this is shielded. So what we have is we call it a shielding cone. So it looks like this. I'm going to draw benzene on its side. Going through the center, and this would be, again, it's kind of shaped like a, well, what would you call this? Call it a shielding cone. And I'm going to draw it in red here. Anything that falls in this area is going to be shielded. Anything that falls on the outside is going to be de-shielded. Yes?
The outside, is it de-shielded or shielded?
Excuse me?
Are they both shielded or?
Inside here, this is the donut hole. If you look.
On the other notes, on the.
I see. Gosh, I keep doing that. This is de-shielded. Thank you. Sorry about that. All right. The drawing is correct. We have a shielding cone and we have a de-shielding cone. The proton on a benzene ring is falling into the de-shielding cone, the de-shielding area, and that's why we have such a large chemical shift. So this moves all the way down, chemical shift usually greater than 7. Questions on the shielding cone for benzene? Anybody? Yes?
On the outside induced, is that supposed to be field? I don't understand.
Induced magnetic field.
Oh, magnetic field.
Yes. All right, so the proton on benzene, we usually don't have protons here, do we? But people have made compounds where we have a long carbon chain here that goes from one side to the other that falls right in the shielding cone, and those compounds like that, I can look up one for you and show you next time. Very, very low chemical shift. Very, very low, even negative. You'll see negative chemical shifts for protons that fall right in the shielding cone. All right, so we have the same thing that happens anytime we have a pi bond. So we're going to have some unusual effects here. So here's a carbon-oxygen double bond. And you can see that in the center here, these arrows are going this direction. Outside, the arrows are going this direction. So outside, the induced magnetic field reinforces the external field. Induced magnetic field reinforces the external field. So this is de-shielded. And here the induced magnetic field, so H induced. Is the opposite of HO. So this is de-shielded. Shielded, sorry. Boy, I'm having trouble with that word today, aren't I? Okay, so we have a shielding cone for a carbon-oxygen double bond. It looks like this. If we draw this on its side, this going back, we don't normally draw this way, but I want to try to draw it so that it's kind of perpendicular to your page. Here's our shielding cone. I'm going to show you for an aldehyde here. So here's shielded, shielded, shielding cone here. And then outside this area is all de-shielded. All these green areas, de-shielded. All right, so what we see for aldehydes, and that's why we see aldehydes, the proton that's bonded to an aldehyde has chemical shifts greater than 9. Why so high? It already has the very strong electron withdrawing group carbonyl, pulling electron density away, and on top of that it has this magnetic anisotropy which is adding to that. So very, very, very high chemical shift, very, very de-shielded. All right, same thing goes for alkenes. Here H effective is lower. On the outside here, H effective is larger. When H effective is larger, it's de-shielded. So for an alkene, we have the same idea going on here. Here's our carbon-oxygen double bond, again, laying on its side. So we're going to draw dashes and wedges. It's kind of perpendicular, floating above your page. And the shielding cone is right here. Of course, outside is deshielded. Outside this cone is deshielded. And if we have a hydrogen bonded to an alkene, it's in the deshielded area. So that hydrogen right there is deshielded. So we have the same effect. This is moved downfield. Chemical shift 5 to 6, not as far downfield as an aldehyde, because aldehyde still also has that very strong electron withdrawing group of the carbonyl, which we don't have here. All right, and now we can explain why an alkyne is much lower than we would expect. And that has to do with the way that the electrons are circulating. So what we know about an alkyne, I'll just draw it right here. We have our sigma bonds here. We have our 2 pi bonds, one in the y-axis, the other in the z-axis. And rather than us just having circulating electrons for this pi bond and for this pi bond, I've drawn these really skinny. They're much fatter than that. We actually have electrons circulating in this direction. So all of those pi bonds overlap. So we have circulating electrons. So it makes kind of like a tube of circulating electrons here. And so we actually orient our molecule differently. So here's the carbon-carbon triple bond. There's the electrons circulating around. So when we get our ring current is going perpendicular to where it is here. And so that's going to change what happens here. So for an alkyne, here's our shielding area, H effective lower. And outside, H effective is greater. So our shielding cone for an alkyne looks a little differently. We have the alkyne actually buried in the shielding cone. So here's our shielding cone for an alkyne, very different here. I should have made that a little taller here. We'll just leave it like that. So there's our shielding cone, outside deshielded. And so the hydrogen that is bonded to an alkyne is deshielded. I mean, it's shielded. So in spite of the fact that that carbon is more electronegative and should be moving that downfield, that happens to fall right in the shielding cone. So that's why for what we see for alkynes, chemical shift 2.5. Questions on magnetic anisotropy, anybody? All right, one more thing I want to say before we stop here, and that is that protons attach to heteroatoms. So atoms other than carbon are highly variable and sometimes absent. This is very solvent dependent. So when we take an NMR, we put our compound in a solvent, and here's our common solvents. And you'll notice something that these all have in common here. CdCl3, D2O. This is deuterated DMSO, CD3 for both of those. Those are the most common solvents. What do they all have in common? No protons. That's important because if we put our compound in a solvent with protons, we'd never be able to see our compound because it would be so drowned out by the protons in the solvent. So this allows us to see the solvents. We will stop right there and we'll talk more about this next time.